Okay, so in this video, I want to talk about exponentials for Drinfeld modules. Okay, and so I'm just going to state a theorem. So it says for each Drinfeld module, and so here we're going to work over, we're going to work in equicharacteristic P, and so this is C again is so we take FQ 1 over T, we algebraically complete this, and then we p-adically complete where we do, or T inverse adically complete. Okay, so for each Drinfeld module over C, there exists a map, and this is going to be the exponential map associated to the Drinfeld module from C to C, and so this is going to be a rigid analytic map such that the following diagram commutes. So here we're just going to have multiplication by capital T, and then here we're going to apply the exponential, and then here we're going to have the Drinfeld module map associated to T. So i.e. This is a morphism with the trivial Drinfeld module. Of rank 0. Okay, so this map here is going to be the exponential associated to the Drinfeld module. Okay, so this is the theorem. Maybe another thing that's useful to write down is the functional equation for this. So you can unwrap this, and what this really just says is that here, if we do t times z, this really becomes here phi t of phi of z. Okay, and so this is really like a transcendental thing. Let me give another example. Or let me just give a single example. Okay, so let rho be a Drinfeld module over C, be the Carlitz module. Okay, so again, this has the property that for rho t of z is equal to z to the q plus t times z, for z and c. So in this case, the exponential is the function, this following function, x rho z. So this is the sum to infinity of q to the j over dj. Okay, so this is called the Carlitz exponential. Here, dj is equal to I, so I minus 1 to the q, all the way down to 1 to the qi minus 1, where this thing here is t to the q to the I minus t. And so you can see that this thing is just going to be, oh, so this is with J's. J. Okay. J. And then this is, so you can see that this is going to be J times D J minus 1 to the Q. Okay, so there's kind of this recurrence between these things. Okay, so this is this thing here, and this function is called the Carlitz exponential. And I want to prove this. I want to make this claim. I want to prove that this is actually, this function here is the exponential for the Carlitz module. So the proof that performs as advertised. Okay, so so let's just make some notation. Let's say E of Z. So I don't have to write it down. So this is just going to be a shorthand that we're going to use. And the proof is really straightforward. So so what do we need to show? We need to show that E of t times z changes into ez to the q plus t times ez. So for all z and c. And to do this, we're just gonna kind of use the functional, or use the formula. So this is tz q to the j over dj here, 0 to infinity. So this is tq to the j q j over dj here, and then okay, so that's one thing. The other thing that we have is t ez. So this is just, well, this exact same thing. Sum from j is equal to 0 up to infinity of t times z to the q to the j over dj. So if we subtract these things, we get e tz minus t e to the z. So this is a sum from j is equal to 0 up to infinity. And now, what do we have? We have t to the q to the j minus t divided by dj z to the q to the j, like so. Okay, and now we can use, so let me call this star. We can use the recurrence here between the d's, like so. So this really uses nothing. So this really says that star, so this thing here, star is equal to sum from j is equal to 0 up to infinity of, so now we have 1 over dj minus 1 to the q. Okay, so all I used is this formula here. So I took this is what we had, this is parentheses j over here, okay, to the q of z to the q to the j. So we can really write this as q to the j minus 1 to the q. Since we're working in characteristic p, we can bring these out, and we have what? So I can do z to the q, let's say, sorry, z to the q j minus 1 over dj minus 1 here. This whole thing should be to the q. So I think I'm forgetting an index here somewhere. Well, then this would tell us here, this is equal to, this would tell us that etz minus tez is equal to ez to the q, or that ETZ EZ to the Q plus TEZ. Okay. And that would prove the result. So what am I missing here? So so the index from j is equal to 0. So this kills the first term. So when j is equal to 0, this becomes this. So this is just 1 here. Okay, and so this is a 1, and this is a 1. Okay, now everything's okay. All right. Okay, so that just proves that this Carlitz exponential is the exponential for the Carlitz module. All right. So the next thing I want to show is so how do we think about exponentials? Okay, and the important thing to think about is the periods. Okay, so so definition. Okay, let phi be a Drinfeld module over C. Then the lattice of periods of phi is defined to be, so this is going to be this lattice here. It's defined to be this kernel of the exponential associated to the Drinfeld module, and this is contained in C. Okay, so let me just say, let me give you a lemma real quick. So we can prove really easily that this is an A module. Okay, here again, A is this, what we always do is FQ of T. So this is like the integers. This plays the role of the integers in the rigid analytic setting. This is a characteristic rigid analytic setting. And so, so let's do the proof real quick. Okay, so this thing here is clearly an abelian group. Okay, so that's free. And we need to show that it's a module now. So let A of T be an element of A. So again, this is this ring. Then we can take the exponential associated to this of, so let me actually just do this on the next page. So let lambda be here. And what can we do? Well, we can take the exponential of phi of A of lambda here. And so now since this is a group homomorphism, an additive, so a morphism of modules, so what it does is it changes this, sorry, this is a T here. It changes this multiplication into multiplication for the Drinfeld module. And this is, again, by the definition of Drinfeld modules, so this is phi of A of T applied to the exponential here. And this is 0. This is equal to 0. And so this is equal to 0. Okay, then this shows that, so this implies that it's an A module. An A module. Okay, that's pretty easy. Okay, so this is the period module, and so so let's look at the idea is to think about. So the idea about this in the same way we think about the periods for, let's say, GM of C or an elliptic curve. And so let's just recall some things. So let's say here's the setup. Before we do this, here's the setup for Drinfeld modules. So the setup for Drinfeld modules is the following. Okay, so we're going to have our rigid analytic complex numbers. We have this exponential map here, and then we had this kernel. So this is a map of additive groups. We had this guy here, 0, this is the lattice here. And what it does is, this is multiplication by t here. So this is the stupid multiplication by t, and it's converted into the Drinfeld module multiplication here. So this is the other module map. And so this is x here. So this is what gives us the morphism of modules, and then I guess we can just say that this whole thing is equivariant, like so. And so this is kind of the diagram that you use a lot. All right. So and again, this is kind of the trivial Drinfeld module. It's not really a Drinfeld module because some people require the Drinfeld modules to have rank bigger than 0. But and then maps between Drinfeld modules are usually maps between Drinfeld modules of the same rank. But you can kind of still think that this is a map. This is certainly a map between endomorphism modules. All right. So this is the thing, and I said that this is going to be like the map for elliptic curves. So the setup elliptic curves. So we're going to have a similar setup. So here we have this map from C to E of C to 0 here. And so this is the exponential for the elliptic curve. So this isn't the exponential at the identity, but another one. So let me just kind of finish this diagram out. And what I could say here. So this is multiplication by, so for a fixed t, here. So this is multiplication by an element. So here we have z goes to t times z, and we can say that maybe t is some number in C, representing a point. And then here is going to be the kind of elliptic curve addition. Curve. Okay, so we have this thing, and this map here, x e of z, so this is the Weierstrass exponential, where this map, this thing here, is this crazy function plus the sum. This is not equal to 0. 1 over z minus 2m pi 0 minus 2m pi 1, let's say n, squared minus 1 over 2m pi 0 plus 2m pi 1 squared, like so. And I guess I need to do some other notation here. So E, so this elliptic curve, once we have this, E is going to be defined by some Weierstrass equation. Y squared is equal to 4x cubed minus g2x minus g3. So this is the actual equation here. And here, this thing is going to be, so this is x of z and this is y of z. Okay, so we have these two functions, and then they satisfy this equation. And then here we're going to do, actually, once we do this, we're going to get the elliptic curve multiplication. And so these pi 0 and pi 1s, what are these things? So pi I, these are the periods, and so these look like the integral of xi of dx over, actually, gamma I, square root of 4, and then we have x cubed minus g2x minus g3. Okay, and so these are the period integrals, and so these are the periods, and then the lattice associated to E is generated by by pi 0 and pi 1. And so these elements are in here. So this is the lambda. So lambda is equal to z pi 0, z pi 1. Okay, and these are the periods. And maybe I can say a little bit more about what these are. So in order for this to make sense, you need to do branch cuts. So you need to take loops in the complex plane. Around branch points. Okay. All right, so those are what the periods are. And that's how you go back and forth between these. Okay, so this is kind of the picture that we should be thinking about when we're looking at the Carlitz exponential, or not the Carlitz, the Drinfeld module exponentials. So we're going to get some periods here, and so this exponential should be thought of as something like this exponential here. I mean, another important thing is another thing to think about is that we can do also this setup for the multiplicative group. This is kind of a similar version. So here we draw the same picture, C, and then we have this exponential map. This is the usual exponential map here. And when we do it like this is just multiplication by t for some fixed t and z. So here z maps to t times z. And then here, so we have z, and this is maybe something raised to the tth power. So z maps to z to the t. Okay, so this exponential, the usual exponential, converts this structure, so this C module structure, into this C module structure. And then the kernel of that is the periods, the usual periods. Okay, and again, this thing is the usual exponential map. What is this? To infinity. Just the usual exponential. Okay, so the important analogies to keep in mind. Okay, first, so the Carlitz module, well, I am just going to say this, it behaves like GM. So the diagram before is, okay, so look, I mean, I'm just going to say that without specifying. Okay, and then rank 2, Drinfeld modules behave like elliptic curves. Okay, so for one example is that if you have a rank 2 Drinfeld module, again, these things are the Drinfeld modules of the form t tau 0 plus g tau plus delta tau squared. When it degenerates, so you can make a moduli space of these, and the degeneration at the boundary of these will degenerate into the GM ones, so the Carlitz module. Okay, and this is similar for the degeneration of elliptic curves into multiplicative groups. Okay, so I want to talk about now that I've kind of said this, I want to say a little bit about the periods of the Carlitz module. Okay, so let me just stop here, and then I'm going to do another video on the periods of the Carlitz module.